Hello everyone, my name is Naina and I'm from the Buddha Academy. So today we will see the last part of hydrocarbons, that is aromatic hydrocarbons. So in our previous videos we have seen about alkenes and alkynes. Today we will see about the aromatic hydrocarbons, basically the compounds with benzenes. Now these hydrocarbons are also known as arenes. Okay, now alkanes, alkynes, we call them as aliphatic hydrocarbons. These are aromatic hydrocarbons and they are also known as arenes. Now since most of them possess pleasant odor, they have a quite good smell. In Greek, aroma means pleasant smell. Okay, now the class of compounds was named as aromatic compounds because of the smell they have. Now most of such compounds are found containing a benzene ring. Okay, so most of the aromatic compounds, they are found containing a benzene ring. The benzene ring is highly unsaturated, but in majority of reactions of aromatic compounds, the unsaturation of benzene ring is retained. Okay, so benzene is highly unsaturated, but in a reaction which includes aromatic compounds, okay, the unsaturation of benzene is retained, it doesn't change, okay, it doesn't distort. However, there are examples of aromatic hydrocarbons which do not contain a benzene ring but instead contain other highly unsaturated rings. Okay, now there are compounds which doesn't contain your benzene but some other highly unsaturated rings. Now, aromatic compounds containing benzene ring are known as benzoids. Okay, the compound which contains benzene ring are called as benzoids, and those not containing a benzene ring are called as non-benzoids. Okay, some examples are given below. These are the examples, that is benzene, toluene with a methyl group, this is naphthalene, this is biphenyl. Two benzene rings are joined together, so it's a biphenyl. Now, nomenclature and isomerism of benzene rings. Nomenclature and isomerism of aromatic hydrocarbons has already been discussed in your previous unit. Now all 6 hydrogen atoms in benzene are equivalent, so it forms one and only one type of monosubstituted product. Okay, when 2 hydrogen atoms in benzene are replaced by 2 similar or different monovalent atom or groups, 3 different position isomers are possible. Okay, 1, 2 or 1, 6 is known as ortho, 1, 3 or 1, 5 is known as meta, 1, 4 as para. So you know that ortho, meta and para substituted. Okay, this we have seen in the organic chemistry chapter. Now a few examples of derivatives of benzene are given below. This is methyl benzene or toluene. This is 1,2-dimethyl benzene or orthoxylene. Okay. Then 1,3 is metaxylene and 1,4 is paraxylene. The structure of benzene. Benzene was isolated by Michael Faraday in 1825. Now the molecular formula of benzene is C6H6. Indicates a high degree of unsaturation. Okay, because it has 3 double bonds associated with it. Now this molecular formula did not account for its relation to corresponding alkanes, alkenes and alkynes. There is no alkanes, alkenes or alkynes which are with this molecular formula. Okay. Now due to its unique properties and unusual stability, it took several years to assign its structure. Okay, so since benzene has a unique property and it has an unusual stability, it is stable with its electronic configuration, with its structure and all, so it took several years to assign a perfect structure to a benzene ring. And then benzene was found to be stable molecule and found to form a triazonide, which indicates the presence of 3 double bonds. Okay, so benzene was found to be stable molecule and it was found that there is a triazonide which indicates the presence of 3 double bonds. The benzene was further found to produce one and only one monosubstituted derivative, which indicated that all 6 carbon and 6 hydrogen atoms of benzene are identical. Okay, so it was found that there is only one monosubstituted derivative is there, which has 6 carbon, 6 hydrogen atom, which are identical. Okay. Now, on the basis of this observation, Auguste Kekulé in 1865 proposed the following structure of benzene, having cyclic arrangement of 6 carbon atoms with alternate single and double bonds and 1 hydrogen atom attached to each carbon atom. So later this structure was reduced by Kekulé. Now the Kekulé structure indicates the possibility of 2 isomeric 1,2-dibromobenzenes. Okay, so because of the structure, it indicates the possibility of 2 isomeric 1,2-dibromobenzene. In one of the isomers, the bromine atom are attached to the doubly bonded carbon atom, whereas in the other they are attached to the singly bonded carbon atom. Okay, they can be attached to any of them. Here it will be attached to doubly bonded, here it will be attached to singly bonded carbon. Okay, see, either attached to doubly bonded or attached to singly bonded. Now, however, benzene was found to form only one ortho disubstituted product. This problem was overcome by Kekulé by suggesting the concept of oscillating nature of the double bonds in benzene as given below. So, since they form this similar structure, this problem was overcome by Kekulé. He suggested that the double bond, they keep oscillating. Keep oscillating means they circulate around the molecule, and this is your resonance. Okay, now even with this modification, Kekulé's structure of benzene fails to explain unusual stability and preference to substitution reaction and then addition reaction, which could later be explained by resonance. So even though Kekulé had given this structure, he wasn't able to explain the stability, preference to substitution reaction and addition reaction, which was later explained by resonance. Okay, now resonance and the stability of the benzene. According to valence bond theory, the concept of oscillating double bond in benzene is now explained by resonance. Okay, even though Kekulé said that there is a oscillating double bond, but the concept was perfectly explained by resonance. Now, benzene is a hybrid of various resonating structures. Now, the two structures A and B, okay, the two structures A and B given by Kekulé are the main contributing structures. Okay, these are the main contributing structures. The hybrid structure is represented by inserting a circle or a dotted circle in the hexagon as shown in the C structure. So, these are the actual or the main contributing structure. Now, the hybrid structure, you can either show them with a dotted circle or a circle in the hexagon. Okay, these are the hybrid structure. The circle represents the 6 electrons which are delocalized between the 6 carbon atoms of the benzene ring. Now, the circle is the one which represents the electrons. Okay, they are moving from one bond to another. Now, the orbital overlapping gives us better picture about the structure of benzene. Okay, see here you can see the better structure of orbital overlapping of benzene. Now, all the 6 carbon atoms in benzene are sp2 hybridized because they are forming double bond between each of them. So, they are sp2 hybridized. Each of the carbon attached to the benzene rings are sp2 hybridized because they have double bond. If it is triple bond, then it is sp hybridized. If there is only single bond, then it is sp3 hybridized. Okay. Now, the two sp2 hybridized orbitals of each carbon atom overlap with sp2 hybrid orbitals of the adjacent carbon atom, form a 6 C sigma bonds. Okay, so it is something like this. They form an head-on-head overlapping. Now, the remaining sp2 hybrid orbital of each carbon atom overlaps with s orbital of a hydrogen atom to form the CH sigma bond, 6 CH sigma bonds. Okay, this 6 hydrogen atoms. Okay, all these carbons are overlapped by sp2 sp2 hybridization, and these are CH hybridizations. Okay. Now, each carbon atom is now left with one unhybridized p orbital, which are perpendicular to the plane of the ring as shown below. So here you can see there are sigma bonds which are formed, and these are the unhybridized p orbitals which later now the unhybridized p orbitals of the carbon atom are close enough to form pi bonds by lateral overlap. Now by lateral overlap they forms the pi bonds. Okay. So this 1, 2, 1, 2, 3. Here you can get a fourth one. Okay, so this is 1 double bond, this is 2, and this is 3. Okay, you can get 3 double bonds and 3 single bonds between. Now the structures shown corresponds to the calculate structure with localized pi bonds. Now the internuclear distance between all the carbon atoms in the ring has been determined by the X-ray diffraction to be the same. So the distance between the carbon atoms in the ring has been determined by X-ray diffraction, and it is considered to be the same. Now there is equal possibility for the p orbital of each carbon atom to overlap with the p orbitals of adjacent carbon atoms. Okay. This can be represented in the form of two donuts. Okay, these are the of electron cloud. Now one of the above and one below the plain hexagonal ring as shown here. So this is the hexagonal ring, one electron cloud here, one electron cloud here. Now the 6 pi electrons are thus delocalized and can move freely about the 6 carbon nuclei. Now instead of any 2 or A or B, the delocalized pi electron cloud is attracted more strongly by the nuclei of the carbon atom than the electron cloud localized between the 2 carbon atoms. Okay, the 6 electrons are thus delocalized and can move freely about the 6 carbon nuclei instead of any one. But the delocalized pi electrons could attract more strongly by the nuclei of the carbon atom than the electron cloud localized by the 2 carbon atoms. Now, therefore, the presence of delocalized pi electrons in benzene is more stable than the hypothetical cyclohexatriene. Now, the X-ray diffraction data reveals that benzene is planar molecule and had any one of the above structures of benzene. Being corrected, 2 types of C single bond lengths were expected. However, X-ray data indicates that all 6 carbon bonds lengths are the same order, which is intermediate between the carbon single bond, carbon double bond. Okay, so even though using X-ray diffraction data, benzene compound is considered to be planar and it can have both the structures. Okay, now the bond lengths of carbon were expected. Okay, but however 2 bond lengths for carbon-carbon single and carbon-carbon double bond were expected, but when we calculated it using X-ray data, it indicates that the length of carbon-carbon single bond and carbon-carbon double bond is 139 picometers, which is an intermediate between carbon-carbon single bond and carbon-carbon double bond. Now thus the absence of pure double bond in benzene accounts for the reluctance of benzene to show addition reaction under normal condition, and this absence of pure double bond, it reduces the account for benzene to show an addition reaction in normal conditions, thus explaining unusual behavior of benzene. Next is aromaticity. Now benzene was considered as parent aromatic compound. Now the name is applied to all the ring system, whether or not having benzene ring, possessing following characteristics. So the benzene was considered as parent aromatic compound. Okay. Now the name is applied to all ring systems, whether or not having benzene ring, possessing the following characteristics. So planarity, complete delocation of pi electrons in the ring, presence of 4n plus 2 pi electron in the ring, whereas n is an integer. Now this is often referred to as Huckel's rule. Okay, if all this is there, then the benzene ring is considered, the naming is considered with benzene ring. Now some examples of aromatic compounds are benzene, cyclopentadienyl, cycloheptatrienyl cation. Okay, this is naphthalene, this is anthracene, and this is phenanthrene. Okay, phenanthrene. Now preparation of benzene. Benzene is a commercially isolated form from coal tar. Okay, benzene, it is commercially isolated from coal tar. However, it may be prepared in the laboratory by the following methods. First one is the cyclic polymerization of ethyne. Then cyclic polymerization of ethyne we have seen in the ethyne part. Right, I'll show you again. See, this cyclic polymerization of ethyne will give rise to benzene. Okay. The next one is the decarboxylation of aromatic acids. Now sodium salt of benzoic acid on heating with soda lime gives benzene. Okay, when you have sodium salt of benzoic acid, when you heat it with soda lime, it gives you benzene. So this is sodium salt of benzoic acid, sodium hydroxide, soda lime, it will give you benzene and sodium carbonate. Next one is reduction of phenol. Phenol is reduced to benzene by passing its vapor over heated zinc dust. So this is phenol. With zinc, when you heat it, you get benzene and zinc oxide. Okay. The next is the properties. First one is physical properties. Aromatic hydrocarbons are non-polar molecules and are usually colorless liquids or solid with a characteristic aroma. Here they all have an aroma. Okay, they are colorless liquid or solids. Now you are also familiar with naphthalene balls, which are used in toilets and for preservation of clothes because of unique smell of the compound and the moth repellent property. So you can get you keep naphthalene balls in your toilets and for preservation of clothes, where because of the unique smell of that compound there is no moth which comes. Okay, it acts as a moth repellent. Now, aromatic hydrocarbons are immiscible with water but are readily miscible with organic solvents. Now they burn with sooty flame. Okay. Now, chemical properties. Arenes are characterized by electrophilic substitution reaction. However, under special conditions, they can also undergo addition and oxidation reaction. Now, electrophilic substitution reaction. The common electrophilic substitution reaction of arenes are nitration, halogenation, sulfonation, Friedel-Crafts alkylation and acylation reaction, in which attacking reagent is an electrophile. Now, these are the reactions that we will be seeing. These are electrophilic substitution reaction involving nitration, halogenation, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation reactions. Okay. Now first let's start with nitration. A nitro group is introduced into benzene ring when benzene is heated with mixture of concentrated nitric acid. When you add concentrated nitric acid with benzene, a nitro group is introduced onto the benzene ring, mixture of concentrated nitric acid and concentrated sulfuric acid, which is a nitrating mixture. Okay, concentrated nitric acid and concentrated sulfuric acid is considered to be a nitrating mixture. When you mix it with benzene ring at a temperature of 223 to 233 Kelvin, you add a nitro group onto the benzene ring. That is, you produce a nitrobenzene. That is nitration. Next one is halogenation. Halogenation is the addition of halogen. Arenes react with halogens in the presence of Lewis acid like anhydrous FeCl3, FeBr2 or AlCl3 to yield haloarenes. So whenever you react halogens, okay, in the presence of Lewis acid, that is anhydrous FeCl3, FeBr2 or AlCl3. Okay, benzene halogen in presence of anhydrous AlCl3, you will get chlorobenzene. You add halogen onto the benzene ring. Next one is the sulfonation. Sulfonation is the replacement of a hydrogen atom by sulfonic acid group in a ring is called sulfonation. So when you replace a hydrogen atom with sulfonic acid onto a benzene ring is called sulfonation. That is carried out by heating benzene with fuming sulfuric acid. So you take benzene, fuming sulfuric acid, heat it, you get benzene sulfonic acid. So this SO3H is added to your molecule onto your benzene ring. So this is what sulfonation is. Next one is the Friedel-Crafts alkylation. So when benzene is treated with alkyl halide in the presence of anhydrous aluminum chloride, alkyl benzene is formed. Okay, so when you have a benzene and you have an alkyl chloride in presence of anhydrous AlCl3, you form an alkyl benzene, that is a toluene, thiolbenzene, methylbenzene, whichever alkyl chloride you have, that alkene group will be added onto your benzene ring, okay, in presence of anhydrous AlCl3. Next one is the Friedel-Crafts acylation reaction. Now the reaction of benzene with an acyl halide or acid anhydride in the presence of Lewis acid yields you acyl benzene. Okay. Now when you have a reaction with acyl halide, okay, or acid anhydride, this is acetyl chloride, then you have an O here. Okay. In presence of Lewis acid, that is your anhydrous AlCl3, FeCl3. Okay. So a benzene ring, acid chloride, in presence of anhydrous AlCl3, you heat it, you get a acetophenone. Okay, you get an acyl benzene. Now if excess of electrophilic reagent is used, further substitution reaction may take place in which other hydrogen atoms of benzene ring may also be successively replaced by the electrophile. So if you have excess of electrophilic reagent, you can further substitute the reaction. Now little amount will replace only one hydrogen, but excess will replace all the 6 hydrogens also and add up your electrophiles instead of that. For example, benzene on treatment with excess of chlorine in the presence of anhydrous AlCl3 can be chlorinated to hexachlorobenzene. Okay, so in excess of Cl6, excess of Cl2 in presence of anhydrous AlCl3, dark and cold, you can replace all the 6 hydrogens with Cl molecules. So you can form hexachlorobenzene Cl6 in place of C6H6. Mechanism of electrophilic substitution reactions. So according to the experimental evidences, Se is the substitution, E is electrophilic. Reactions are supposed to proceed via following 3 steps. So in general, all the electrophilic substitution has these 3 steps: generation of the electrophile, formation of the carbocation intermediate, and removal of the proton from the carbocation intermediate. First, let's see the generation of electrophile, that is your E+. Now during chlorination, alkylation and acylation of benzene, anhydrous AlCl3 being a Lewis acid helps in generation of electrophile like Cl plus, R plus, Rc plus O, that is acylium ion, respectively, by combining with the attacking reagent. So all those reactions, your chlorination, alkylation, acylation, they all have anhydrous AlCl3 in them. This is a Lewis acid which helps in the generation of electrophile. Okay, electrophile, like in chlorination you have Cl plus, in alkylation you have R plus, in acylation you form acylium ion, okay, respectively, with combining with the attacking reagent. So here it is shown. So Cl breaks, one of the Cl goes with AlCl3, it forms AlCl4 and a chloronium ion is formed. Again, both the electrons are taken by the chlorine and it goes to the AlCl3 forming AlCl4 and leaving your alkyl ion or your carbocation. Then here also this Cl takes away everything and form your acylium ion. Now in the case of nitration, the electrophile nitronium ion, that is NO2 plus, is produced by transfer of proton from sulfuric acid to nitric acid in the following manner. Okay, so this is what happens in chlorination, alkylation and acylation. For nitration, okay, the N plus O2 is formed by transfer of proton from sulfuric acid to nitric acid in following manner. Means step 1 is you add sulfuric acid and nitric acid, right? Now in step 1 what happens, the electrons from oxygen are transferred to the hydrogen and this bond is transferred to the sulfur, so it forms a plus sign here. And later again both the electrons are taken to the protonated nitric acid. What will happen? It is HNO3, no? So protonated nitric acid, what will do? It will transfer both the electrons onto oxygen, attaining a nitronium ion. So this is the process where you get a nitronium ion. It is interesting to note that in the process of generation of nitronium ion, sulfuric acid serves as an acid and nitric acid as a base. Even though both are acid, highly concentrated acid, but in this reaction, sulfuric acid acts as an acid, whereas nitric acid acts as a base. Thus, it is simple acid-base equilibrium. Okay. Now we have your electrophile generation. Now let's form the carbocation. Okay, or the uranium ion. Now, attack of electrophile results in the formation of sigma complex or uranium ion. Okay, whenever an electrophile attacks, it forms the sigma complex or the uranium ion, in which the carbon is sp3 hybridized. Okay, so benzene ring will attack your electrophile. Okay, when your electrophile is attacked, the double bond breaks. Okay, once the double bond is break, the electrophile will go with one of the hydrogen and the other molecule will get a positive sign. So sp3 hybridized carbon. The sigma complex uranium ion. So this is the sigma complex uranium ion. Now the uranium ion gets stabilized by resonance. So what will happen? This double bond will come here. This positive sign will go here. Okay, so it will undergo various resonance. Overall, what will happen? The positive sign will come in center and there will be a double bond this thing. The sigma complex of uranium ion loses its aromatic character because delocalization of electron stops the sp3 hybridized carbon. So sigma complex or the uranium ion, it loses its aromatic character. It loses one of its double bond from the 3 double bonds because of the delocalization of the electron, which stops at the sp3 hybridized carbon. Okay. Now, next one is the removal of proton. Okay, now to restore the aromatic character, sigma complex releases proton from sp3 hybridized carbon on attack by AlCl4 in case of halogenation, alkylation and acylation. Okay, now, whenever you have an sp3 hybridized carbon, okay, so to restore the aromatic character, the sigma bond releases proton from sp3 hybridized carbon on attack by AlCl4 in case of halogenation, alkylation and acylation, and HSO4 in case of nitration. Okay, so the AlCl4 which is formed at the end, what will happen? It will release a proton which will be taken up by the benzene ring to satisfy its sp3 hybridized carbon, and hence it will form an HCl and AlCl3. Okay, so this is how the nucleophilic substitution reaction takes place. Now next is the addition reaction. Okay, now under vigorous conditions, that is at high temperature and or pressure in the presence of nickel catalyst, hydrogenation of benzene gives cyclohexane. Okay, so under vigorous conditions, that is at high temperature and of pressure in the presence of nickel catalyst, hydrogenation of benzene gives cyclohexene. Now that is dihydrogen with your benzene, nickel and heat, you get a cyclohexene. All the double bonds are removed. Now, under ultraviolet light, 3 chlorine molecules add benzene to produce benzene hexachloride, which is also called as gammazine. Okay, here all the double bonds are removed and replaced by the chlorine molecule, which forms benzene hexachloride, that is BHC. Okay, the next is combustion. Okay, when heated in air, benzene burns with sooty flame, producing CO2 and H2O. Okay, so when we heat it in the air, benzene burns with a sooty flame, producing carbon dioxide and water. So H6 oxygen forms carbon dioxide and water. Now, general combustion reaction for any hydrocarbon may be given by the following chemical equation. Okay, now directive influence of a functional group in monosubstituted benzene. When you have a monosubstituted benzene, is subjected to further substitution. The 3 possible disubstituted products are not formed in equal amounts. So when you have a monosubstituted benzene, is subjected to further substitution. 3 possible disubstituted products are not formed in equal amounts. 2 types of behavior are observed, either ortho and para products or meta products is predominantly formed. It is also been observed that this behavior depends on the nature of the substituent already present in the benzene ring and not on the nature of the entering group. This is known as directive influence of substituents. Reason for ortho, para or meta directive nature of groups are discussed below. Now, whenever you have a substitution of benzene groups, okay, if it is monosubstituted, you can have only 2 kind of substitution, either ortho-para products, okay, or meta products predominantly. Okay, either you will have only meta products or you can have a meta-para, ortho-para products. Okay, everything combined you will never have. So first one is the ortho-para directing groups, which are the groups which direct the molecules into ortho-para directions. The group which direct the incoming group to ortho-para positions are called ortho-para directing groups. As an example, let us discuss the directive influence of phenolic OH group. Now, phenol is resonance hybrid of following structure. So when you have a phenol, okay, this is the resonance structure of phenol. So it is clear from the above resonating structure that the electron density is more on ortho and para positions. So you can see the electron density, it is on ortho position, on para position, again on ortho position. There is no meta position here. So the electron density on the resonating structures is more on the ortho-para positions. Hence the substitution takes place mainly at these positions. So because of this, the substitution it takes place mainly on the ortho-para position. However, it may be noted that one effect of OH group also operates, due to which the electron density on ortho-para position of the benzene ring is slightly reduced. Okay, minus I. Okay, effect of OH group also operates due to the electron density on ortho-para positions of the benzene ring is slightly reduced, but overall electron density increases at this position of the ring due to resonance. Okay, so due to resonance, the electron density increases at the ortho-para positions of this ring. Now, therefore, OH group activates the benzene ring for the attack by an electrophile. Okay. Now, other examples of activating groups are NH2, NHR. These are the other ortho-para directing groups. Now, in the case of aryl halides, halogens are moderately deactivating because of their strong I effect, strong inducting effect. Overall electron density on benzene ring decreases. Okay. Now, because of their strong inductive effect, overall electron density on the benzene ring decreases on the halogens. Now, it makes further substitution difficult. However, due to resonance, the electron density on ortho-para position is greater than the meta position. And because of the resonance, the electron density on ortho para position is greater than that of the meta position. Hence, they are also the ortho para directing groups. Okay, resonance structures of chlorobenzene are given below. So these are all ortho para directing groups. Now, which are the meta directing groups? Now, the groups which direct the incoming group on to meta positions are called meta directing groups. Okay, and some examples of meta directing groups are nitro, cyano, aldehyde, ketones, carboxylic acid, ester groups. Okay, these are the examples of meta directing groups. Let us take an example of a nitro group. The nitro group reduces the electron density in the benzene ring due to its strong inductive effect. Now, because of their strong inductive effect, the nitro group, it reduces the electron density on the benzene ring. Okay, now nitrobenzene is a resonance hybrid of the following structure. Now, these are the structure of resonance of nitrobenzene. So you can see that. Okay, so the nitrobenzene, they have a resonance structure here. Now, in this case, the overall electron density on benzene ring decreases because further substitution difficult. Therefore, these groups are called as deactivating groups. Okay, so because of the electron density, overall electron density of the benzene ring decreases, further distribution or further substitution is difficult. Therefore, it is called as deactivating group. Now, the electron density on ortho para position is comparatively less than that at the meta position. Okay, so the electron density on ortho para position is comparatively less than that of meta positions. Hence, the electrophile attacks on the comparatively electron-rich meta position, resulting in meta substitution. The next one is the carcinogenicity and toxicity. The benzene and polynuclear hydrocarbons containing more than two benzene rings fused together are toxic and said to possess cancer-producing carcinogenic property. So when benzene and some of the polynuclear hydrocarbons, when they contain more than two benzene rings, okay, fused together, joined together, they are considered to be toxic and possess a cancer-producing carcinogenic property. Such polynuclear hydrocarbons are formed on completely on such polynuclear hydrocarbons are formed on incomplete combustion of organic materials. Okay, when you incompletely convert your organic material like tobacco, coal and petroleum, they enter into human body and undergo various biochemical reactions and finally damage your DNA. So thus these molecules enter into human body and undergo various biochemical reactions and finally a damage to your DNA and cause cancer. Some of the carcinogenic hydrocarbons are given below. For example, your 1,2-benzanthracene, okay, 3-methyl colanthrin, benzpyrene. Okay, these are some of the examples of carcinogenic hydrocarbons. So with this, we are done with the chapter hydrocarbons, where we have discussed about the aromatic hydrocarbons. Thank you for watching my video. Please do like, share and subscribe to our channel.